let me briefly introduce him. He finished his PhD in Princeton University under supervision of Professor Nathan Seiberg in 2004. After that, he spent his research career at several distinguished institutes. He did a postdoc at APCTP in Trieste, and then Paris with Marie Curie Fellowship. Then he moved to Amsterdam as a senior research fellow. And finally, in 2013, he moved to King's College London as a faculty member of Maths Department. And now he is in a full professorship position. And in 2015, he awarded the prestigious ERC Consolidator Grant, and he is actively now driving his research area. He is one of the pioneers on black holes in string theory and holography, and also its relation to mathematics. He is not only a great researcher, but also a great teacher. In the department, he several times awarded Best or Excellent Supervisor Award. And since he is currently Senior Advisory Group member of APCTP, so he will at some point visit APCTP. Then we will be able to have good interaction with him. So today, he will give very interesting talk about black holes, holography, and phase of gauge gravity. And please enjoy and please start.
All right. Thank you very much. Thank you for the invitation, and it's a great pleasure to give this talk, and it's a great honor to be invited to this forum along with the other speakers. And thank you, Murthy, for the kind introduction. My title is Black Holes, Holography, and Phases of Gauge Theory. This story really begins with the pioneering work of Bekenstein and Hawking in the 1970s. Let me just make sure I'm being heard properly.
Yeah.
So Bekenstein and Hawking in the 1970s, they were thinking about black holes in the quantum theory, and their work led to some very deep questions about the nature of space-time and of quantum gravity, which has been extremely influential even today. So any putative theory of quantum gravity that we want to build, indeed the ideas of Bekenstein and Hawking are very important constraints on these theories, as I will try to explain. In another direction, their work has gone on to influence fields which I think even they wouldn't have imagined is possible, including things like quantum computation and quantum information theory. But today I will stick to sort of the line of thoughts of the original ideas, and I would like to describe how there's been quite many developments in string theory in resolving the original puzzles and questions. Okay, and of course the reason this is possible is that in string theory we can make very detailed models in which we can study a quantum black hole with precise calculations. Okay, so this is what I'll try to show. Of course, these models depend on the details of string theory, and I won't have time to show all of that. But I'll try to abstract some lessons, at least in the little corners that I have worked on myself. Okay? But already I can say one thing is that the language that seems to be emerging should be familiar to many physicists, namely that semiclassical gravity is emerges as the collective phenomena of some large number of underlying degrees of freedom. Okay, and that's what my title phases refer to. Can you see my pointer when it moves?
Yes, yes.
All right, I'm just going to close the window. All right. Okay, so so these new developments I'll try to introduce in the second half of the talk, and in the first half I'll talk about of the basic ideas that go into the story. It's a very big story, and I'll necessarily be cutting corners. So please do feel free to interrupt if something is not clear. If you have comments, questions at any point of time, that will help me a lot. Okay, so let's begin with the fact that we do not have a direct microscopic probe of quantum gravity. Okay? What I mean by this is that we're not able to build a large graviton collider, which will probe the details, microscopic details of space-time. That is impossible with current technology. So in the absence of such a direct microscopic probe, how do we study quantum gravity? Well, this is not a particularly new situation in physics. In the late 19th century, physicists who were studying gases were in more or less the same situation. They knew that a gas was something inside a box. Okay? They didn't know that it had microscopic structure, and they could measure macroscopic parameters like pressure, temperature, energy, entropy, and so on. And they could calculate empirically, they could calculate relations between these macroscopic parameters. And based on these empirical macroscopic observations, they could make important deductions about the underlying microscopic theory. Okay, for instance, the famous Gibbs paradox, that they could deduce that the particles should be indistinguishable in the quantum theory, okay, or that there should be a cutoff on the energy excitations. Okay. And there are many other such deductions that they actually made. And I note that this is well before, or a little bit before, the advent of the quantum theory. Okay. And these kind of studies led to the following type of questions. So firstly, the most direct question is, what is the microscopic structure of gases? It clearly showed that there is microscopic structure. What is it? And the other type of question is, you have these macroscopic parameters. What happens when you change them? Okay, and this, of course, was developed a lot later in the 20th century, namely that you have phase transitions. Okay, and together, these kind of investigations led to what we currently refer to this whole body of knowledge and theories, which we call quantum statistical mechanics. Okay. All right. Now, why this historical analogy? Well, it's because in the 1970s, Bekenstein and Hawking realized that black holes are thermodynamic objects. Okay, and that leads to very similar questions. Okay, so this is an artist's impression. This is just to attract one's attention. I'm going to drop this picture very soon. So there are very similar questions. Before discussing the questions, let me just make some comments about the fundamental discovery itself. Okay. So what's a black hole? A black hole is, well, firstly, it's an object out there in the sky. As recently there have been spectacular verifications of, you have these black hole mergers. We hear literally the chirps of the ring down. But once all these complicated dynamics have died down, what a black hole settles to is the solution that's described by general relativity. Okay? That's how we understand it as theorists. And these solutions are very simple. Okay, they're completely described by the only conserved quantities, mass, charge, and angular momentum. Okay? So in some sense, it's a very smooth or featureless object. There's no microstructure to it in classical gravity. Okay, this is formalized by the no-hair theorems of GR. Okay. Now, what Bekenstein and Hawking are saying is that in the quantum theory, black holes are actually much more complicated, like a piece of coal, and this simplicity arises only as an average, okay, only in thermodynamic limit. Okay. Now, what's the argument for the fact that black holes have thermodynamics? The arguments are actually very simple. The first argument is because of Bekenstein, who asked the following question. I think it was his thesis problem, actually. That if you have some universe with a black hole in it and you throw something into it, okay, something that carries energy and entropy, okay, a bucket of water or an elephant, okay, then what happens to the loss of thermodynamics? Okay, so firstly, you lose once the bucket of water crosses the event horizon. Yeah, I should say something which I'm sure all of you know, but just to put ourselves on the same page. So in classical general relativity, a black hole is defined as some region of space-time, which is surrounded by this one-way surface called the event horizon. And it's one way in the sense of causality. Okay, it's a very Lorentzian concept that things can fall in, nothing can fall out. Okay, these solutions are the ones that I was discussing here. All right. So once this bucket of water crosses the horizon, then you lose energy from the outside world. But correspondingly, the black hole energy increases. So the first law of thermodynamics goes through as it is, energy conservation. But the second law, it seems to be a problem, because apparently you lose entropy from the outside world, and that apparently violates the second law of thermodynamics unless you assign an intrinsic entropy to the black hole itself. Okay, so this was this very simple sort of thinking of Bekenstein. It was extremely profound, and then he also argued that the entropy must be proportional to the horizon area, the surface area. Okay. And then, well, Hawking said, well, if there is an entropy and an energy, then there must also be temperature. So we must be able to calculate that. And he set up this beautiful calculation where he scattered particles of a black hole using quantum field theory, and showed that the reflection spectrum that comes out precisely matches a thermal object. Okay, so that's how he calculated the temperature. And the answer was this: the temperature is this value here, proportional to h bar, and inversely proportional to the mass. So indeed, in the classical theory, you don't have any such effect. And then when you integrate this integrate the first law with this temperature, you find this famous Bekenstein-Hawking area law, that the entropy of a black hole is a quarter of the horizon area in Planck units. Okay, it's a very beautiful equation involving all three fundamental constants of physics: h bar, g Newton, and c. Okay, so let's, so I'm sure all of you knew that, but I just wanted to briefly review that. Let's get back to this, our main story. Okay, so black holes have temperature and entropy. And from that, follows the same kind of questions that we have for gases. So because a black hole has entropy, just like the air in this room, what's the microscopic structure? What are the atoms of a black hole? Okay. And the second question is, if you study
elementary question.
Please.
Elementary question. In the previous formula, is there a Boltzmann constant or?
Excuse me. Thank you very much. There should have been a Boltzmann constant here. I dropped it. Thank you very much. I put it to 1, and in fact, I'll do that throughout the talk. Thanks a lot.
Oh, okay. Thank you.
Yeah. So it involves actually 4 constants. Yeah. All right. So firstly, what's the microscopic structure? And the second type of question is that if you study the black hole of inside some universe, and you change the macroscopic parameters like temperature or chemical potential, what happens? Okay. Are there phase transitions? Okay. And these, we hope that these kind of questions will inform us about whatever the theory of quantum gravity is. All right. So now I want to sort of explain these 2 questions in a little more detail. Unless there are any other questions, I'll just pause for a few seconds. All right. So please do interrupt. As I said, it's extremely useful. So let's go to the first question. So one thing I want to say is that the 2 types of questions here, if you think about it from the point of view of thermodynamics or statistical mechanics, have to do with 2 different ensembles. Okay, so the first question is, you really want to study a black hole as an object, as an independent quantum system. So that's more like the microcanonical ensemble. You just want to study that thing and ask what it's made up of. The second question is more that you want to place the black hole in some bigger environment and then change the parameters of the environment. Okay, so that's like a grand canonical ensemble. Okay, so this is the small difference that I want to emphasize that we'll discuss now. Okay, so first let's do the microcanonical ensemble. All right. So this is this, let's go back to this area law. Okay, you have some black hole parameterized by its charges, and this area is a function of these charges. And then if you juxtapose this, if you combine this with the Boltzmann equation, and indeed here there should be a K Boltzmann as well, then you find that this semiclassical black hole entropy should be equal to the logarithm of the number of microscopic states of that system in the thermodynamic limit, okay, when the black hole becomes very large. Okay, that's what I've shown here by these dots. Okay. Now this Bekenstein-Hawking law, area law, one of the big features of it is that it's universal. It applies to any black hole solution in general relativity. But this universality is actually self-limiting, because if you want to study the quantum theory of gravity, we think that it must go beyond weakly coupled general relativity. So this law is not going to teach us about that. Okay, if you want to study quantum corrections to GR, we must look at these corrections to the area law. Okay, that will deviations from the area law will teach us about deviations from GR. Okay, that's our interest. So we want to try to set up formalisms where we can study and calculate these corrections. Okay. Now suppose you have such a formalism, then the question is, how do you test it? Okay. And in order to test it, you need a setup where you have an independent understanding of the microscopic degrees of freedom. If you have that, then you can do both calculations and check if you're on the right track. Okay? And that's exactly what is provided to us by string theory. Okay, so the reason string theory does that is because there are actually two pictures of black hole in string theory. Okay, so the first one is this macroscopic picture. Here's the some black hole, which is some solution of GR plus low energy fields, and it has an event horizon. And there's some quantum numbers, n, which here I've taken to be only one integer. This is a certain solution that I'll discuss later in the talk. Imagine some black hole labeled by 1. Think of n as the energy of the black hole. Okay. Now in string theory, there's a parameter called G string, which in supersymmetric vacuum, I'll discuss what that means, you can tune. Okay, G string is a free parameter, and that's what allows you to get this other picture. So the fact is that Newton's constant in string theory is proportional to G string square, and therefore, when G string is much larger than 1 over n, you have this usual picture of a black hole. But when G string is much smaller than 1 over n, then G Newton becomes very small. That means that the Schwarzschild radius becomes smaller than the Compton wavelength of the fundamental objects of string theory. Okay? So if you then know what this ensemble of charges are made up of, this could be strings or branes or whatever fundamental objects you have, the correct description is just fluctuations of these, which can be described by weakly coupled quantum field theory. Okay, gravity is turned off in this picture. Now, in this beautiful piece of work, Strominger and Waffa, they found a setup where they could describe both sides with control. And here, the area of the black hole is 4 pi times square root of n. And here they could count how many states there are as a function of this integer. And they found that as n goes to infinity, indeed, the number of microscopic states is e to the pi square root of n, therefore verifying the Boltzmann equation for black holes in string theory. Okay, so this is one of the big successes of black holes in string theory. Now, what we want to do is to take this setup, and you ask, well, now can we calculate these corrections? Okay. So notice that here, in principle, if I give you some string theory setup, and if we study that enough, then you can make a list of states, and you ask how many states there are. So this is, in principle, an exact number. It's an integer. I'll show you some examples. So the question is really about the right-hand side. Okay, so how do I? Yes.
Because in the right-hand side, what is n?
Good. So this I will describe in great detail. So that here there is a map. So you should think of n for now as just some parameter of the black hole. Okay, so think of n as being, let's say, the mass of the black hole. And remember that the size of the black hole is proportional to n to the mass, and therefore when n is large, the black hole is very large. That's the thermodynamic limit. So you have some asymptotic flat space, and inside you have a very large black hole. What we want to study is deviations from the thermodynamic limit. These are like finite size corrections. Okay, so you want to ask what happens, what are the 1 over n effects?
I see.
Yeah. And when we actually map the models, that n takes on a meaning of certain parameters, certain coupling constants in the theory. Okay, so right now you can think of it as the size or the curvature of the event horizon. All right. So the real question is, can we calculate this at finite n? Is there some notion of a quantum gravitational entropy defined in the gravitational theory, which we can calculate and see whether it agrees? Okay. So this is the kind of question that we would like to address. This is the first type of question. Okay, any other questions about this setup? All right. So now let me move to the second type of question, which is about the grand canonical ensemble. Okay, so this will take a little bit of time to explain the basics. So please bear with me because there's quite some history here. All right, so grand canonical ensemble. So now so the first question was, we took a black hole here and asked, and it had some parameter n. We asked, we want to ask how many microstates or what's the quantum entropy. Now, in the second type of question, we want to place the black hole in some bigger system. Okay, what does that mean? In order for that to be consistent, it means that if you perturb the black hole a little bit, those fluctuations of energy should also be contained in your ensemble. Otherwise, it's not a good ensemble. Okay? And in the theory of general relativity, what that means is that you take the metric and write down fluctuations and ask how it dies down. It's a question about boundary conditions, that those fluctuations should be allowable in your theory, in the boundary conditions that your theory and that you impose on the theory. Okay? Now, this is a very subtle problem in general relativity, and in flat space, this has so especially in flat space, it's a subtle problem. So you have asymptotically Minkowski space. So this is some infinity both in space and time. You ask, what kind of fluctuations am I allowing? So clearly you should allow particles, but are you allowing other types of energy excitations? And this is sort of a whole field of research started by the group of Bondi and collaborators at King's, actually. And even today, there's intensive research in that. And it's a very subtle problem. So we want to avoid that. So what other type of universe can we put the black hole in? So there's, asymptotically, you think there's no matter. So you can either have zero curvature, or you can have positive curvature or negative curvature. So zero curvature, as I said, is subtle. Positive curvature is even more difficult because then you have a problem in the de Sitter space of observer dependence and the fact that the spatial slices are compact and things like this. But anti-de Sitter space, the space of constant negative curvature, is the perfect framework for this. Okay? And the reason that's true is because if the nature of infinity in general relativity in anti-de Sitter space, this is in the sense of Penrose, if there are experts there. Is that it's a space-like object. Okay, so there's some here I've taken 5-dimensional AdS5 gravity. You can take a space-like slice. There's time there, and infinity is what is called conformal infinity. So it's a very large spatial manifold. In this case, I've taken to be the 3-sphere. Okay, so this is 5-dimensional. There's a 3-sphere. It's a radial direction which goes inside, and there is time. And here, if you analyze the fluctuations of the metric of AdS5, you'll see that it's very easy to put boundary conditions with just decay as you go to this spatial infinity. Now, this fact was realized by the pioneers of black hole thermodynamics. This is not at all new. This was realized in the 70s. And people were studying, because of this, they started to study black hole thermodynamics in anti-de Sitter space. Okay, so in particular, if you put a black hole in anti-de Sitter space, the whole AdS space acts like a box because of this potential well, okay? And there are small fluctuations. You can study the grand canonical ensemble. This was also work of Hawking and others, and Gibbons and Page and others. I'll discuss that, which at that time wasn't, it caught the, I think it attracted the attention of people who were studying GR, but not probably, a much bigger community. That came a little later. I'll explain this. So the moral of the bottom line here is that we want to study, so black holes in anti-de Sitter space is the right place to study the grand canonical ensemble. Okay, and this is true for anti-de Sitter space of dimensions 3, 4, 5, and so on. Okay, dimension 2 is a little subtle, and it doesn't apply. Okay, any questions about this?
Can I ask? Then, in fixing boundary condition, then what does it correspond to in terms of ensemble?
So exactly, good. So that's exactly what I'm going to go to next. So just bear with me for one slide. So I'll just tell you a brief answer and ask me again if it's not clear. It corresponds to fixing the conjugate potentials. So like the temperature or chemical potentials. Okay, that's exactly where I'm headed next. Okay, so how do we study thermodynamics? Okay, so here is this black hole, okay, of some mass m. And if you want to study, so first let's look at the metric of the black hole. Okay, so the metric of the black hole is like this. It's minus g of r dt square plus dr square over g of r plus some angular direction. Okay. If you've taken some basic course in GR, you would have seen this metric, at least in the context of Schwarzschild black hole in flat space. Okay, in that case, g of r is 1 minus 2m over r. And this is 2-dimensional. Now we are in 5-dimensional space. So g of r is 1 minus 8gm over r square. And because you're in ADS space, you have this extra factor. Okay, so when the curvature of the ADS goes to 0, this extra factor disappears. Okay. And as we all know, this function is what determines the horizon. So the horizon is an intrinsically Lorentzian concept. It's the place where the light cone flips, and T and R, what used to be time-like and space-like, change their properties. And that happens exactly when G of R becomes 0. So that's the horizon. Now, to study thermodynamics, what one does is exactly what one does in usual statistical systems. Suppose you're given a statistical field theory. And let's say you want to study equilibrium thermodynamics. How would you do it? Well, you take time and you compactify it in the imaginary direction with some period, which is 1 over the temperature. That's the radius. So do exactly that at infinity. So let's go on. What happens? Well, the metric, so what used to be a minus sign here becomes plus because T goes to IT. Okay. This circle becomes compact. It's now, you have a fixed temperature. And now let's see what happens to the horizon. So because G of R is the size of the circle, if you draw this in the Euclidean, the Euclidean manifold corresponding to this, now I've drawn it like this as people like to draw it. So the idea here is you draw time as a fibration over space at every point in space. Okay, so at infinity, you have an S3. That's what this is. This shows. And as you come in the radial direction, the S3 starts shrinking. Okay? And the time circle correspondingly starts shrinking. And at the horizon, it goes to 0. Okay, so you get this cigar-like manifold. And at that horizon point, the S3 has some finite size, and that's the horizon sphere. Okay, that's the Euclidean manifold that we're studying. All right. So here, where exactly it shrinks depends. So you have some fixed boundary size, I mean boundary conditions, beta, and then you have to solve the Einstein's equations and ask what is a smooth manifold. Okay, and then these conditions fix the energy, the location of the horizon, which tells you where is the value of the mass, and so that gives you a relation between the temperature and the mass. Okay, that's the thermodynamic relation. That's how the gravitational thermodynamics works. Okay. In fact, does this answer your question?
Yeah, thanks.
Yeah. Okay. And now, there's this famous principle of Gibbons and Hawking and Perry, which says that, so they asked, well, okay, you have this nice setup. You have a black hole with, I've called the mass equal to energy. A black hole with energy and temperature and entropy. So can we write what is the canonical free energy? So go to the canonical ensemble, fix the temperature, what's the free energy? Okay. The answer is that the free energy is the Euclidean, is the action of this Euclidean solution that we just wrote. Okay. By action, I mean that, so you have to study some theory. These are solutions to, let's say, general relativity. So you have the Einstein-Hilbert action. Okay. And you have to ask, what's the action of this manifold evaluated on this solution? Of course, this action is infinite because in this direction, this area space goes up to infinity. Here, I've just shown some kind of an asymptotic conformal boundary. But you can say, what is the action of this black hole with reference to, let's say, empty areas? Okay, that's one way to regularize this. You can calculate this, you get some function. This is some number divided by G Newton divided by beta cube. Okay, this will pick up later. And the observation of Gibbons and Hawking is that this on-shell action acts exactly as beta times the free energy of the system. Okay, what does that mean? It means that energy and temperature are conjugate variables with respect to this free energy, and the entropy is given by the Legendre transform, by this variational principle. Okay, that's how we study thermodynamics in the canonical. Okay. And this principle is called the quantum statistical relation, is very general. So instead of just mass, you can have, let's say, a black hole with mass and spin and electric charge. If you have electric charge, you should study Einstein theory coupled to Maxwell fields. Okay, and you do the same procedure. Okay, you have this temperature, but now you also need to give potentials with respect to the angular momentum. So temperature was the time component of the metric. The chemical potential for angular momentum turns out to be the off-diagonal dt d phi type of component of the metric. And phi, the chemical potential for charge, is really the potential of this electric Maxwell field. Then you study the system, it's a coupled system, and then go through the same steps, calculate the action. So now you have a different action. And again, all these the charges and the chemical potentials are conjugate variables, and the entropy is given by variational principle. So this is how people calculated gravitational thermodynamics. And I should say that there is something amazing about this. Okay? This is something extremely non-trivial about this, which is that in usual statistical systems, this procedure of compactifying time and calculating, the variational principle or path integral, we understand very well because time is not involved in the story. There's if you have equilibrium thermodynamics, then there's equilibrium everywhere. And then if you have a circle, you have a trace interpretation in the Hilbert space. Here in quantum gravity, we don't have a Hilbert space. And moreover, this notion of a horizon is an intrinsic Lorentzian notion. Okay, that's where the light cone flips. Okay, it's a Lorentzian notion. And thirdly, in this Euclidean geometry, we've completely removed what is inside the black hole. You only see what is outside the black hole. Nevertheless, this prescription of calculating the on-shell action and demanding smoothness seems to give perfectly well the thermodynamics in the semiclassical theory. Okay, this is as I want to stress again, it's a very non-trivial fact, and I think people are still trying to understand this. There's been maybe some small progress about this very, very recently. Okay, we will take this, and this is how we study thermodynamics.
Can I ask questions? In this gravitational action, you have two integral. One is black hole, one is ATS. What is integration of a black hole?
Sorry, what I meant by black hole,
yes.
What I mean here is this manifold. It's the ADS black hole. It's the black hole in ADS space. So it's still asymptotically ADS, but inside there is a black hole. The second manifold is just pure ADS space. Okay. The fact is, if you take this manifold for the black hole and calculate the integral, this is infinity, because on this side, so here there's a cutoff by the horizon, but on the boundary there's an infinity because it keeps growing. That infinity is the same infinity that if you just take pure ADS5 solution, you also have the same kind of asymptotic boundary condition. So you subtract the two. Sarah?
I see. You are subtracting pure ADS part.
Yeah. So that's so by this I mean the ADS black hole solution. By this I mean pure ADS.
I see. Thanks.
So in fact, that's exactly where I'm going to next. So you have these two. We know. So we want to do this. Yeah. Yes, please.
In the previous slide, I think I didn't catch what do you mean non-trivial? I mean, this sounds natural, but what do you mean non-trivial? Sorry.
Yeah. So it sounds very natural. Right? This is what you would do in statistical field theory, right? You just calculate the action of the you compactify time in the imaginary direction, and you do the path integral, or in the semi-classical limit, you just calculate actions. I want to stress that in usual statistical field theories, time just decouples from the problem if you have equilibrium. It's just there is no dynamics. Here in gravity, what happens is you can do that at infinity. Okay, infinity, you can say that it's static. But the very notion of a black hole involves time. It's a very Lorentzian concept. So it's a very different, yeah. Yeah, is that clear?
But if I consider some quantum statistical mechanics, it's usual to take time in Euclidean formula.
Yeah. Which is why Gibbons and Hawking did that. They said, let's do what is done in quantum statistical mechanics. And it works. But in quantum statistical mechanics, you can, once you take the path integral, you can cut open the time direction, insert a resolution of identity, and you have a trace interpretation. So you have an explanation of why that gives you, and then you can do, you can get your Kubo formula, you can get Matsubara frequencies, things like this, okay, because you're going around the time circle. Here you don't have that luxury because you don't have a Hilbert space into which to take the trace. And as I said, you're not even seeing inside the black hole. This is just the space outside the black hole, but still it works.
I see.
Okay, so that's a bit of a mystery.
Okay, yeah. Let me consider more about it. Okay, thank you. Yeah.
Okay, now let's get back to this thing Imtak was asking. So you have these two solutions. So think of this as a path integral, and the best we can do for this thermal path integral is, you do some saddle point approximation. So when G Newton is very small, path integral means you solve the equations of motion. Okay, that's the gravitational action to solve the equations of motion. And we know two solutions. One is empty ADS, one is the ADS black hole. Okay, maybe there are other solutions. Okay, and then there might be some quantum fluctuations around each saddle. That's okay. But already you can do a lot. And this is this famous Hawking-Page transition. What can you do? Write these two solutions. You can almost do it visually, but you have to do a small calculation. So this is the black hole we were discussing. So there's a time circle, and it goes, and then it becomes 0 at the horizon. The other ADS solution is like this. You have the at infinity is the same, S3 times S1, but now it's just empty. So it's just empty ADS. So the circle just does nothing. There's an infinite, there's a tube which goes on, but the space circle just shrinks smoothly to a point. So this is just pure ADS. So that means that in the Euclidean theory, the spatial size just becomes, it's like the two-dimensional plane when the circle just shrinks to a point. Okay, that's exactly what's going on. Okay, so in one case, the S3 shrinks, in the other case, the S1 shrinks. And now you can ask, which of them has more action? Okay, the one which has sort of least action or least free energy will dominate the ensemble. Okay, so for instance, you can fix the size of S3 and vary the size of S1. So let's take this as a reference and now vary the size of S1. So if the size of the circle is very large, then when you solve the Einstein's equation, the curvature is very small. It's going to take a long time before which it turns back. Okay, this is like a variational problem. That means it has a lot of volume and therefore a lot of action. If the circle size is small, then it's going to stop very quickly and turn back. Okay, so that means that at high temperature, when the circle size is small, it's the black hole phase that dominates. It has least free energy. And at low temperature, it's the empty ADS that dominates. And this can be made very precise. There's a transition. You can calculate the transition. You can calculate these actions and ask what is the transition temperature. Okay, this is the famous Hawking-Page transition. All right. So, any questions about this? All right.
So I have a small question.
Yes, please.
Is it easy to see from the black hole metric that the beta decreases to 0 at the horizon? I mean, the radius of the S1 decreases.
Definitely. So here it is. So let's look at the metric. Oops, there we are. So notice, remember, what is G of R? So if you remember basic G of R is the point now in the Lorentzian theory where the light cone flips. Light cone flips means that the role of the sign of T and the dt square and dr square must flip. So G of R is positive outside the horizon, goes to 0 and flips sign. Right? It's 1 minus 2 over R. So where G of R equal to 0 is the horizon. Now let's do the same thing in the Euclidean theory. G of R multiplies dt square. That means it's in the metric, in the Euclidean metric, it's the size of the circle. So when G of R equal to 0, that's the horizon. Yeah.
Okay.
Yeah. So this is of course for a non-spinning black hole. For spinning black holes, you have to do a little more.
Okay. Thanks.
All right. Any other questions? Okay. So now I want to ask. So that was sort of a long history of prehistory of black hole thermodynamics. So how do you test these ideas? In order to test these ideas, the ideal place to do so is the ADS CFT correspondence. So you have this ADS space, okay, as usual, as we've been considering. And now the ADS CFT correspondence says that there is a dual non-gravitational theory, which is exactly equivalent to this. So it's a 4-dimensional theory. If this is ADS 5, this is 1 dimension less in 4 dimensions. It's a gauge theory which lives on the conformal boundary. So in this case, it's an S3 times time. Okay, and it's a conformal field theory. So let's take, the prototype example is what is called n equal to 4 super Yang-Mills theory. So there's a Yang-Mills theory in 4 dimensions with 4 supersymmetries in the minimal representation. What that means is that there is a certain fermionic symmetry. Minimal representation has 4 components. So n equal to 4 means that there are 16 supercharges. And that means that the gauge field comes in multiplets. So there's a gauge field, there are gauginos, and there are scalar fields. And there's an extremely well-defined action. And there are 2 parameters of the theory. One is the gauge group, which you take to be SUN. So the parameter is n. And the second parameter is G Yang-Mills, the coupling constant. Or you can replace that by what is called the 't Hooft coupling, okay, G square times n. Now, in this prototype example, so here so far we're just studying pure gravity in ADS 5 or Einstein-Maxwell theory. Here it's a slightly more complicated theory. It's called type 2B string theory, which is defined on asymptotically ADS 5 spaces. But in fact, secretly, it's a 10-dimensional theory. It's a string theory. So there's a compact S5, which I've not drawn here. You can think of this as a reduction to 5 dimensions. And this theory also has two parameters. One is the Newton's constant, and one is the length scale of the ADS space. Okay, and in that, there are black hole solutions. The theory has two parameters and two parameters. And the ADS CFT correspondence gives a dictionary, gives a map between the parameters. So lambda is L to the 4th. And importantly, G Newton is 1 over n square. And then the way the correspondence works is when this Etov coupling is very small, you have the usual notion of, when Etov coupling is very small, you have the gauge theory. You can study perturbation theory with Etov diagrams. And when lambda is very large, then you have weakly coupled gravity. Okay, so here, keep your eyes on this equation that G Newton is 1 over n square. So this is one of the questions that was asked. So here's a little more detail. Okay. Now, in this beautiful paper of Witten, it was shown. So what was done was the following. So you take this setup that I just said, ADS CFT, and now you study thermodynamics. So again, compactify the time circle. So there's some temperature, and write down the basic equation that the partition functions on the two sides must be the same. Okay. So on the gravitational side, this partition function is, this semiclassical notion. There's a sum of saddles with some gravitational action, like we just saw. But on the gauge theory side, you have a much better control over the quantum theory. You have a Hilbert space of the theory, and you can do a trace over the Hilbert space, and the thermal partition function is literally a trace of e to the minus beta times the Hamiltonian of the theory. Okay, all this is completely well defined, and you can write down an expansion in energy eigenvalues. Okay. Now, you want to compare these two notions of a partition function. They're both conceptually and calculationally very different, but the ADS CFT correspondence says they're the same. So now you ask for the phases. Well, at low temperature, we already saw that in ADS space, there's just empty ADS plus maybe some fluctuations. And in gauge theory, we know that at very low temperature, you ask what is the phase of the gauge theory, just a vacuum, maybe plus some glue ball excitations. This is pure gauge, which are all singlets. Okay, so the entropy is very, very small, and the free energy is of order 1, even as you scale n to infinity. At high temperatures, you have a completely different picture. On this side, on the gravitational side, we saw that you had this black hole plus maybe fluctuations of gravitons. And on the gauge theory side, you have this famous deconfinement transition. Okay, and it was this beautiful observation that the Hawking-Page transition maps to the deconfinement transition in gauge theory. Okay, so deconfinement means at very large temperatures, all the n square degrees of freedom. So remember, it's a matrix valued. The fields are matrix values of n square degrees of freedom. They all deconfine, and you have some plasma of gluons, and if there are quarks, there are also quarks. And so the free energy goes as n square times. Now remember, this is a conformal field theory. So if you ask what's the energy of a conformal field theory at a certain temperature, this is a very easy calculation. It's the kind of thing we do in StatMech courses. It goes as temperature to the 4th. Okay, that's your beta to the 4th. And here, remember, you have to calculate this free energy was given by the beta times the free energy was the on-shell action, and there was this calculation that I showed you. Okay, so this was one of the big pieces of evidence for this kind of matching. Right? So this finishes the review of the second type of question. And what we want to do now is to take these ideas, these templates that were given to us, and we want to do better. We want to ask, can we make this more precise? Instead of these kind of scaling arguments, can we actually calculate some partition functions or entropy more precisely, more exactly in any given system? Okay, that's where I'm headed next. And for this, we'll introduce supersymmetry. Well, let me pause for questions, and maybe I'll sit down. Okay. All right, so let's go on. So supersymmetry. So what is supersymmetry? So the basic idea of the basic supersymmetric system is this. You have some quantum system with a fermionic charge, Q. It's complex. is that QQ bar anticommutator is the Hamiltonian. Right? Now you write representations of this. It's well known. This side is positive, definite, the left-hand side. So you can, H is either positive or 0, which if H is positive, you divide by H, and you get the basic Clifford algebra, for which the representation is two-dimensional. Okay, so you have, for the same value of H, you have two states, one of which you call a fermion, the other one is a boson. Or when H is 0, you can have Q on the state is also 0 and Q dagger is 0. So you have these states which have 0 energy. These are called supersymmetric states. Here, there's not necessarily any pairing. Okay, you can have singlet states. So the basic representations. And now you calculate this thing called the Witten index. It's an observable which is defined on the full Hilbert space. You take a trace over all the states. Is -1 to the f, which is -1 on the fermions, +1 on the bosons of e to the minus beta h. Now, because of this pairing, you see that whenever h is non-zero, you always get a plus and a minus cancellation from fermions and bosons. So in fact, that is independent of beta, and the only contributions come from these supersymmetric states. It's the number of bosons minus number of fermions at 0 energy. Now, the nice thing about this index is, suppose you change the Hamiltonian, suppose you have some coupling constant and you change it in a way so as to preserve the supersymmetry, then the whole spectrum will shift, but it'll always shift, keeping the pairing intact. Okay, so there might be new 0 energy states, or less, but always in pairs, and therefore this number never changes. So this Witten index is invariant under deformation. This is one of the biggest, most important properties. All right. Now, this is what we're going to use, and this is some, just a number that you have. You might say, well, this is a boring observable. In fact, you can refine this this Witten index. You can put operators here, so some chemical potentials taus coupling to some charges which commute with the supercharge, and you can see that the same set of arguments goes through, and you'll get instead of a number, you'll get a function. So function defined on the set of supersymmetric states, which tells you some properties which you give here. Okay, so that's the Witten index. And this Witten index for this sort of baby example counts 0 energy states, but in more sophisticated examples, you can have more supercharges. So for instance, you can have the same algebra repeated n times. And in such cases, there's a simple generalization where you only demand that one of these supercharges annihilates the states that you want. And you can again repeat the same arguments. Okay, these are such states are called BPS states. And now you can have non-zero energy. So a typical example is that you'll have one of the charges which squares not to the Hamiltonian, but to energy minus the charge, for instance. Okay, and therefore, when you say that that is 0, you get that the states obey energy equal to charge. Okay, you generalize from energy equal to 0 to energy equal to charge. Okay, there's some theory with a Maxwell field. All right. So you can measure quite non-trivial features of the theory, and now we want to use this in this setup of going from states to black holes, or from CFT to ADS. Okay. Now, if you start with, so the idea is instead of saying that the states form black holes, you say supersymmetric states form supersymmetric black holes. So that's why you land on this special type of black holes called supersymmetric, or BPS. BPS for Bogomolny, Prasad, and Sommerfeld black holes, which also obey the same algebraic relation, energy equal to charge. So what this means, firstly, is that these black holes are necessarily charged. You can't study Schwarzschild black holes with this technology. And moreover, these black holes are what are called extremal. Extremal means that the temperature of the black hole is actually 0. Okay, there are two horizons in this for these black holes, and they meet each other so that the temperature is 0. So these black holes are not the type of black holes that we see in the sky. However, what this allows us to do is it gives us a lot of control, as you will see, and it allows us to test these basic ideas of quantum gravity that Bekenstein, Hawking, and people since then have been laying out. Okay, what this allows us to do is to test, for instance, is a black hole made up of microstates? We can see this explicitly. Okay, so that's the advantage, and that's the disadvantage. Now, just like the temperature is 0, the other chemical potentials are also frozen. Okay, so it turns out if you have a spinning or a charged black hole, the chemical potentials don't go to 0, but they go to some number. I'll give you some examples. And as a consequence, what happens is that there is no thermodynamics. So usually for thermodynamics, you want beta to be a function of the energy, or chemical potential to be a function of the charge, then you vary it like I showed you. For supersymmetric black holes, you have this very funny behavior that they get frozen. Right? And this, so what it really tells you, this is a bit for the experts, but it's important. What it tells you is that you need a regulator. And understanding this regulator is one of the parts of the progress that has been made in the last 10 years or so in various systems, 10, 15 years. Okay, so when you regulate it, you think of these supersymmetric extremal black holes as some finite temperature black holes, and then you take the limit to 0 temperature. All right. The other subtlety is that this is also a little bit for the experts, that what you're calculating is not quite a degeneracy. It's this index, it's number of bosons minus number of fermions. But in fact, for a large class of black holes, one can show that all the microstates that belong to it are purely bosonic. There are no fermions, and therefore the index equal to degeneracy. Here's a very quick comment I made. This is a long story. You can look at these papers. All right, so any questions about this? And now what I'm going to do is to tell you about more recent developments. Yeah, any questions?
Yeah, a small question. So in the diagram you drew on the ground state, any particular reason for the bosonic states to outnumber the fermionic states?
No. This was just some example I gave you. It could be the other way around. Absolutely.
Oh, okay.
Any other question?
One question more. As far as I know, PPS black hole state is not the same as extremal black hole. So
They're not the same, indeed. Yeah.
so when
Okay. So this is a, okay. This is an expert question. This is okay. So let me try to explain this. So if you look at the, in fact, I was going to put a slide on this, but then I thought it would be too technical. But since you asked, let me explain this. So it turns out that if you, for any black hole, write any supersymmetric theory and write down a solution which is not supersymmetric. Look at the parameter space of solutions. And then you ask, you can do this for the simplest example you can do this is in, let's say, supersymmetric Einstein-Maxwell theory. There's a mass and a charge, and then you can have black holes which rotate in 4 dimensions. Then you ask, what is the smoothness in Lorentzian theory of some smoothness relation? And that turns out to be an inequality. Okay, that relates. So for instance, you'll have that the some relation between energy, charge, and angular momentum. And the BPS, in the sense of let me say extremal black holes, saturate that inequality. Okay, that's one type of condition. The other type of condition is that mass equal to charge, what you see on the screen right now, that is supersymmetry. These two conditions a priori are not the same. Okay, one of them could be it saturates an inequality, and the other one is something like this. So for instance, in 4-dimensional black holes, you'll find that J has to be positive or 0. That's the type of inequality you have. And here you have equilibrium. Now, if you demand that you have supersymmetric black holes, which are also regular, that there are no closed time-like curves, then you land on exactly on extremal black holes. Okay, so that's the story.
I see. Thank you.
Yeah, this is going to be important for us. What happened? So some of the things that happened recently is that one realized that you need a regulator. Not so you don't put regularity in the Lorentzian theory, but you go to the Euclidean metric, which is what we need for thermodynamics. There is no reason to put to demand no closed time-like curves. There's no notion of time there. Okay, and so you can get rid of this other sort of inequality, and so you have a whole parameter space of supersymmetric solutions. Only one of which has a good Lorentzian interpretation. So all of them have good Euclidean interpretations where you can do thermodynamics, and that's exactly what is needed. Your question is needed to calculate a variational principle for supersymmetric black holes. Okay, that's one of the new developments. All right. Any other questions?
So, can you sketch in which case index is same to degeneracy?
Okay, this, if you don't mind, I would like to postpone this. This is a very technical question, and actually, Imtak, you're one of the experts on this. Maybe after I finish, I'll discuss this. Roughly, I'll just give you a brief answer. I think this actually holds for all supersymmetric So all reasonable supersymmetric black holes. But the proof, one can prove it whenever you have a non-abelian symmetry at the horizon. So if you have, SU10, SU2 or SO3 at the horizon, then you can prove it. That's in this paper. This work of Iliesu and Teotoriachi and others in the and Hayden and Maxwell in Maxfield in the recent past, who missing one name, Murat, who showed that even for other black holes where you don't have non-abelian theories, but let's say only U1, there you need more calculation to show it, and case by case you can show it. So my belief is that this will always be true. I'm happy to discuss more after the talk. Okay, so then let me now tell you about more recent, meaning in the last 10 years or so. A little bit behind time, but I'll go as far as I can go, and then please stop me. So the first one is the first question. Okay, so how do we understand black holes as a regular quantum systems? Okay, that's not how they begin their life, but we believe that that's true because of these thermodynamic arguments. Okay. So I'm going to take this prototype example. These are some set of words. I just wanted to say this because it's some concrete example. Take n equal to 8 string theory in 4 dimensions. What that means is that the effective theory is general relativity coupled to 28 Maxwell fields. And then there are some scalars and fermions. And this theory is 32 supercharges. And in this theory, there is a black hole solution, which has been discovered long ago, which preserves 4 of the 32 supercharges. Okay, that's the type of black holes I was discussing. And this carries charges under all the 28 gauge fields, electric and magnetic charges. And these 56 charges are actually rotated into each other by a large symmetry, duality symmetry of this theory. And therefore, there's only one quartic invariant, which you can call n. Okay? And all physical observables should be dependent on this n. And this n is a positive integer. And this is the picture that I'd shown you quite a while ago. Okay, so these black holes are completely labeled by one positive integer. And the area of the black hole is 4 pi square root of n, and therefore the entropy is pi square root of n. So this was known already in the 90s. Now we want to do better. We want to ask, how do you calculate these corrections? Okay, so there's a very large story here. I'm just going to tell you why there are corrections. So the first type of correction arises because of UV physics, ultraviolet physics, short distance physics. And that's because, so the Bekenstein-Hawking area law is a law, thermodynamic law in general relativity. But whatever the true quantum theory of gravity is, I think it's universally accepted that it's not weakly coupled general relativity. There's some kind of extension. It could be string theory, it could be something else. But from the effective field theory point of view, it means that you'll have higher dimensional operators in the action. And in the presence of such operators, these are suppressed by the Planck scale. In the presence of such operators, this Bekenstein-Hawking area law is no longer valid. It doesn't obey the laws of thermodynamics. And it's replaced by what is called the walled entropy. So that's one set of type of corrections. You have to ask, what is the Lagrangian? If you have some string theory framework like we have, you have to calculate this effective action and then calculate this walled entropy.
Elementary question. Can I understand the walled formula somewhat more intuitively?
So the walled formula is, I'll tell you the extent to which I understand it. The walled formula, what Wald and Iyer and Wald asked was they demanded that the first law of thermodynamics should hold. Okay, so you have some setup, and these higher dimensional operators change the nature. Firstly, change the location of the horizon because the solution changes a little bit, and then it also changes. The theory itself changes. So they asked, well, let's sit at infinity and measure things like energy and temperature. Okay, the temperature we fix as usual, and energy you can measure. Okay, energy you can measure in any theory of gravity, asymptotic energy, because asymptotically there is no there's no black hole. Asymptotically it's just, let's say, flat space. So these higher derivative corrections don't matter. You can use some kind of an ADM formula to measure the energy, okay, or its generalizations. And then they demanded that dE dm equals TdS. Okay, that's what gives you this form. That's roughly how they constructed it. that does not show that this obeys the second law of thermodynamics. And in fact, it's still not been proven that this obeys the second law of thermodynamics. In fact, people think that there should be small modifications to this, to this law, and this has not been settled fully.
I see. Thank you.
Yeah. The second law, remember, is a much more complicated thing in GR. You have to solve the Raychaudhuri equation and you know, make sure that the area always increases. Sorry, the entropy always increases. Okay, the second type of effect is infrared physics. Okay, so what do I mean by this? So suppose you have some UV complete theory. This has, you imagine GR plus some massless fields plus lots of massive fields like in string theory to some UV completion. But even if you take the, so you have some Lagrangian, effective Lagrangian, but even for the massless fields, even for a photon, when it runs in a loop, at low energies, there's an effect which is non-analytic, non-local, okay, which is logarithmic, for instance, at the, with respect to the IR cutoff. That gives a big contribution to this entropy. Okay, that's a quantum fluctuation, genuine quantum fluctuation. And this was unraveled by some heroic work of Ashok Sen and collaborators over 5 or 6 years. And the bottom line is that you have sort of a notion of quantum entropy. So remember that exponential of the entropy is like the degeneracy. So exponential of the quantum entropy is defined to be some functional integral in the gravitational theory. So phi is over all the fields of the gravitational theory with whatever Lagrangian you have, and this is some Wilson line operator that you write down. Okay, this is a formal construct because you don't know how to do functional integrals in gravity. But as far as these IR problems are concerned, this is enough. The idea is to set up a functional integral which respects the symmetries of the problem. And for extremal black holes, Sen and collaborators said how to do this. And then they actually used this formalism to calculate the leading log corrections, for instance. All right. Now, you can go further for supersymmetric black holes by using a method called localization. Okay, so this is a method which has been developed for supersymmetric quantum field theory, which implements an enormous reduction of the functional integral. Remember, the functional integral starts as some infinite dimensional integral over field space. And what localization does is it essentially sort of cuts the field space into orbits of the supercharge and then shows that only the fixed points excuse me, contribute. Okay, so in that sense, it reduces. And if you're lucky, sometimes you get finite dimensional integrals. Now this,
my question. Yeah, so in the last slide, why only the massless modes would lead to this? Why not? I mean, why do we not need to consider?
So massive modes you can also integrate out massive modes, but such effects you can always encode in some, when you have, so think about it, suppose you have some string theory, what are the massive modes? The massive modes will have some, Planck scale suppression, okay? Or you might have some KK scale suppression, in which case this should be KK scale. All of those can be encoded in some effective action. And then they're going to be small at very low energy. The effects will be small at very low energies.
Okay.
If you have a photon, then the infrared effect is not small at low energies.
Right. Okay.
Okay. So this is this method, and this has been quite, it's been made rigorous in supersymmetric quantum field theory. And in fact, you can use this method also in supersymmetric theories of gravity, but here there are many both technical and conceptual hurdles. My colleague Imtak is one of the experts, so I should ask him if there are any questions. And this has been developed over 10 years or so. At the end of the day, if you apply, I'm cutting a very long story short, if you apply these methods to this prototype that I showed you, you get some 8-dimensional integrals, 7 of which are Gaussian, and you're left with this 1-dimensional integral representation for the quantum entropy of this black hole labeled by n. Then the answer is this is some Bessel, essentially up to a polynomial prefactor is a Bessel function. Okay, now we understand. So this formula has been sort of checked quite carefully. Right. Now let's look at the microscope. We want to check this. Let's look at the microscopic setup. So it's the same string theory. Now we are in some weakly coupled limit, and you ask what are all the objects of string theory which carries the same charge n? That's yet another sort of series of research problems, and this has been solved. And the answer is that there's some set of D-brane configurations which in a certain frame, duality frame, you can always reduce it to some D-brane configuration. So these are extended objects in string theory, and you calculate the BPS fluctuations. Now you have to count how many fluctuations there are, and instead of sort of showing you the details of this calculation, I'll just do a sort of try to give you a sense of what kind of methods are involved. So the simplest extended object is, of course, a string. You can think of it as a D string. And these D-branes usually wrap some compact cycles in string theory. So think of a string wrapping a circle. Then you ask, what kind of fluctuations can you have? So you have to solve some Laplace equation on the string, and you get various modes of the string. So you can get, the first mode, the second mode, third mode of oscillation, and so on. And the answer is simple. You just have the modes. The spectrum is labeled by integers, into which you can put some energy. And our problem there, therefore, is you have some big energy n, total energy n, and you want to put it into various oscillators. That's really a question of partitions. So you have these oscillators, and this problem is well understood. You write the generating function of oscillators, and then you multiply them out, and what you get is this Dedekind-eta function. So that's a simple toy problem. Instead of this, you can have a fermionic oscillator, you get a theta function. In our case, there are 4 bosonic directions and 1 complex fermionic direction. And what you get is something like this. This generating function of microscopic degeneracies is a function of the charge n, or size n, is some theta function divided by the Dedekind to the 6. Okay, these are the definitions. And here I've expanded it. You should read it as, so there are 2 functions because the even and odd functions behave slightly differently, even and odd charges. So the power of Q here should be thought of as the size and the charge, the size of the black hole. And the coefficient is the degeneracy of microscopic states. Okay? And what we want is the black hole entropy formula really comes at n equal to infinity. So you should look at the asymptotics of this problem. And the one important point here to note is that these functions are not any old functions. They are very special functions called modular forms, which have been studied by mathematicians for more than a century. And they're extremely symmetric functions. So if you write q equals to e to the 2 pi at tau, essentially the function at tau is related to the function at -1 over tau. Okay, that's a very, and it's holomorphic. So it's an extremely constraining symmetry. And there's an infinite set of such transformations given by SL2Z. And in fact, it's so constraining that you can write an exact formula, analytic formula for this d micro. So usually if you're given some generating function like this, you invert it. You say d micro is some contour integral, is some Fourier coefficient of this, a certain q coefficient of this. So, yeah. Okay. And once you have such an inverse Fourier transform, then you can try to do some saddle point approximation and get some integral. You get some asymptotic series. In this case, you can solve those integrals exactly, even non-perturbatively. Okay, so here's the answer. So the answer is that this microscopic degeneracy is written as an infinite series labeled by an integer c. So each term, there's some polynomial prefactor, there's something called a Klosterman sum, which is some small sum over phases, which we'll ignore today, times this modified Bessel function. Okay. And now remember that the Bessel function, for I Bessel function, for large values of argument goes as exponential, and therefore the c greater than 1 terms are exponentially suppressed. So the leading exponential correction is the I Bessel function. And then you can do an asymptotic expansion of it. Okay. These were formulas which were developed by the number theorists. This is Hardy and Ramanujan in the 20s, who had such a formula, but not quite convergent. And then Hans Rademacher, who sort of tweaked it a little bit to get a convergent formula. All right, and it relies on these modular properties of the function. Now, the amazing fact is that this is the same formula I've shown here, is interpreted very easily, very intuitively in gravity. So let's see how that's the case. Remember, d micro is exponential of the entropy. You see, let's begin from the bottom. So here is pi square root of n is precisely the Bekenstein-Hawking entropy of the black hole. The next correction, the first log correction is indeed the leading one loop correction that was calculated for this black hole background. Then you can ask, can I sum up all this perturbation theory in gravity? And that was exactly what we did this localization calculation. You can calculate the first Bessel function using localization, and you get exponentially close to the answer. Okay, there are these higher C terms, which I'll comment on in a second. And let's see how good an approximation this is. So here is the table. So this is n, the size of the black hole, is the number of microscopic states. These are the series that I showed you, 8, 12, 39, 56, and so on. And the last column is the exponential of the Bekenstein-Hawking entropy. And these two columns asymptotically agree. This you can prove analytically. But for small charges, there's clearly a lot of discrepancy. And now here is the table of this exponential of the quantum entropy that we just calculated. And you can see that for small charges, indeed, there's a very good agreement. So this is a calculation of the gravitational sort of quantum, this gravitational entropy, including quantum effects. We've summed up all perturbative quantum effects. And you're essentially seeing an integer, even for small values of n. Okay? So somehow this number theoretic expansions are giving you a very good guide for how gravity sees quantization. It's not that you have a horizon and the number of degrees of freedom is just some cut off of the horizon into some 208 pieces. It's not like that. There's some continuum approximation, and you do better and better, and it sums up to the integer. Okay. So any questions about this?
Can I ask you a question?
Mm-hmm.
Can you go back one slide? Yeah. Is it true that the enlarge and this is negative?
This is it true that what is, I didn't hear the question, is whether
Yeah, right.
this one?
If n is large.
Yeah.
And this is negative, seems.
Oh, so you probably found a typo. It should have been, sorry, this bracket, excuse me, this is a LaTeX typo. This bracket should have been in the exponential. It's a, sorry, log of this should have been pi square root of n times that, and then it's negative. It just shows that it still increases exponentially, and then there's a small, it's not quite exponential, but exponential with a negative power of n. That's what this negative says.
Okay.
Yeah, sorry about that. Thank you for catching that. This bracket, I should have put exponential. It's a LaTeX problem of this whole thing. That's what I meant. Yeah.
Mm-hmm.
All right. Any other questions? Okay.
And also, I mean, this is, I don't know whether, do you have any, I mean, the reason why we meet the, I mean, this Bessel's in this counting problem?
In the, so do you mean microscopic or?
No, whatever reason it is.
Okay, so there are two reasons. So, I mean, well, at least at the level of calculations, I don't know what your question means, but
Yeah,
maybe
right.
you're asking a deeper thing. At the level of calculations, the number theorists tell us that any function of this sort, which has this modular symmetry, which has a small, which starts with a negative coefficient, will always be written as a sum of I Bessel functions. Okay, that's a theorem of Hardy and Ramanujan, and then okay, that's the number theoretic side. What was surprising to us is that our gravitational calculation also gives the same Bessel function. Okay, this comes really from doing some localization calculation, summing up all the perturbative corrections around the black hole. This, I don't have a better explanation than the fact that, it's the answer to a calculation. Okay, so this is the sense. Sorry?
Okay, some integral representation of Bessel.
Yeah. Okay. But this is the sense in which how these kind of number theoretic formulas are a very good guide. It's hard, it's good to say what you're shooting for, and then it helps you to arrange your perturbation series. But also philosophically, as I said, it's the sum of Bessel functions that add up to the integer. So indeed, you can ask now, what about the small exponential corrections? Okay, so here I show the same plot. Now this is a log scale plot. This is a log scale, and so this is the exponential of the. So the dots are the microscopic numbers that I just showed you. This line here is the exponential of the classical entropy. That's this big. That's this line, Red line is the classical entropy plus the first one loop. Okay, and you see that there is a reduction, and this is precisely the minus sign that you asked about. Okay, this is a reduction, but it's still exponentially growing. And the blue line is the first Bessel function. So you can almost, in this log plot, you don't see a difference between the blue line and these microscopic dots. Okay, so but now you've got this under control. Now you can remove the log. You can actually plot what is the actual W micro, the microscopic numbers minus this first, the all order perturbation theory, and you see that you get something like this. You get some function, which even for very large charges, you see the discrepancy is very small. It's 3. And in this paper, which actually came out today, we show how to recover this whole set of orbifolds also from some localization calculation. And that turned out to be quite subtle, and it needed some recent insights into what is called JT gravity and the Schwarzian mode, which have been developed in the last 4 or 5 years. And what we did was to combine this with the old insight of Ashok Sen, and together it all adds up to exactly account for these corrections. So now you can really get this whole integer calculation. Okay, it's a very brief sketch, but I wanted to say that. Okay, so any other questions? So this finishes my first story, but let me ask if there are any other questions, and then I'll give you one more example before stopping. All right. So the second example is now I want to do grand canonical ensemble. Okay, you want to think of this as a collective quantum system, and here we think of ADS5 gravity, like I showed you. So you go back to this ADS-CFT setup. Okay, and now it turns out that in this basic setup, there are black holes which are BPS black holes, okay, which preserve 2 of the 32 supercharges, which have macroscopic horizon area. Okay, and in weakly coupled gravity, you can calculate its Bekenstein-Hawking entropy. And in this part of the story, I will not discuss quantum corrections. All of this is semi-classical. Here, the idea is what happens to the semi-classical physics when you change the parameters, okay, the grand canonical parameters. So, so now we want to account for this. So first, let's do the same kind of accounting that we just saw for these other black holes. The question is, where you want to calculate these 1/16th BPS states. So look for this 1/16th BPS index. It's called a superconformal index in this n = 4 superMS theory. And that had been counted in these papers. And this whole question was asked. They said, well, you have this index. Can you see the entropy of a black hole from this index? Okay, like in the example that I just showed you, like in these D1, D5 examples. All right. So this question was first posed in these papers, and that led to a lot of research for the last almost 20 years. And recently there's been progress. There's been many contributors to this. And I won't list all of them. Please look at the papers where we have references. And this is really a collective effort from the community. And now we understand that indeed, from this superconformal index, you can extract the entropy of the black hole, including all the numerical coefficients. Okay, this was very important because somehow this was puzzling that there is this basic ADS-CFT setup where it's difficult to see this black hole entropy. It's extremely satisfying to have understood this. One of the things that you want to see was that, again, because of the 1/g Newton, there's an n square. Again, you see the reference to this question that was asked, PSOC asked. And can you see this n square scaling from the index? Okay. So what are these black holes? So again, now you have these black holes are labeled by the energy. Now you have ADS5. So the symmetric group of ADS5 has an SO4. So there are 2 angular momenta. There's also a Maxwell field, so there's some charge. But again, the simplest BPS black holes are labeled by 1 quantum number, okay, exactly like in my other story. This is called L. And the entropy of the black holes look like this. Okay, this is L here. Ignore this brown line. And these curves are the entropies for various entropy formulas
for the various ranks. Okay, so of course this entropy is valid when n is very large. So n is n square is 1 over g Newton. Then you can see that indeed there's an n square scaling as you go this way. And then there is some scaling with respect to the gravitational charges. This is the size of the black hole in gravity. As that increases, the entropy also increases to some 2/3 power. Okay. So all this was known, and now now the recent progress has been on the microscopic side to begin with. The counting function is also known. It's slightly more complicated than these modular forms. Now it involves functions, infinite products, which are, if you know your theta functions, you'll recognize that theta functions are like 1 minus q to the n. But here you have 1 minus q to the n to the power n. So there's more growth, there's something more complicated. It's more like a McMahon function, or what is called the elliptic gamma function. And you have to then integrate over some chemical potentials. This is the formula. These functions are not so well studied by mathematicians. Only in the last 20 or 30 years they've been studied. But you can just check, this is the formula, you can check numerically if it works, and indeed there's a spectacular agreement, even for very small n. This agreement, this solid line is the black hole entropy formula, and these dots are the microscopic degeneracies, contributions. So this is the first. So this kind of agreement is the same type of agreement at the level of microcanonical that I showed you in these other black holes. Okay. So you can take this as a starting point. And now we want to study the grand canonical. We want to ask what happens. So clearly the black hole is present in the index, but you want to ask what happens when you change the parameters of the boundary. Okay, so here you see some hints here. You see that, okay, it's a good match. There's maybe some 1 over n effects. You can see that it doesn't quite agree, but more importantly, there's some oscillations here. Okay, so that is trying to tell you something. All right. So any questions so far? All right. Yeah.
Sorry, yeah. This n is 2, 3, 4. It seems it's very small number.
Yeah.
And, is there?
Yeah. So there's a bit of a surprise. Maybe you know the answer to this. There's a bit of a surprise why it works so well at even for such small n. Okay, so I don't think this has been explained completely. So for this, you need to ask the kind of questions I was asking earlier. What are the quantum effects? What this suggests is that somehow the corrections, 1 over n quantum corrections, are highly suppressed.
Yeah, thanks.
All right. So now we want to do grand canonical.
Is it
So
true that the for larger n the deviation gets bigger?
No, the deviation. So there are two things. So first you look at the average value of the dots. Okay, there the deviation becomes smaller.
What is the discrepancy between the real line and this triangular dots? So
so if you average the triangular dots, okay, over some, let's say some window like this, then you get a very close fit to you get a better fit to the line than in n equal to 2. Average is going like this. Look, it's like this. There's a small discrepancy. What you see here is that there's this oscillation around this average. Okay? At scales which are macroscopic, this is n equal to 10 here, you see. And that's something which is worth explaining. Okay, so it's really trying to tell you something, that there is some macroscopic effect here. It's not some 1 over n small correction. You'll see this in a second. Please ask if it's not clear after 5 minutes. So there should be a reflection of this exponential growth in the grand canonical ensemble. So these d of n are these these microscopic integers, and we are studying these kind of generating functions. This is like the partition function, the index of the theory. And if you want, so first let's see if you know this, how do you calculate d of n? Well, you calculate d of n by doing this contour integral. You do 1 over q to the n and dq over 2q, contour integral over 0. If you write q equals e to the 2 pi tau, you translate it into a tau integral. And typically the way you do it is when n goes to infinity, then tau roughly goes to 0, okay, in the saddle point approximation. Then you have to ask what is the behavior of the function f as tau goes to 0. Now, if this is a modular form, then the modular invariance gives you that answer, because tau goes to 0 is mapped to tau goes to infinity, which means q goes to 0, and this can be very easily read off. Okay, and typically, if you want growth, you need some negative. Excuse me, here this should have been from some small negative power. I mean, in other words, there's a small prefactor here, q to the minus some small energy, and the exponential growth of dn comes from the exponential growth of f at tau goes to 0. So, for example, for modular forms, you typically have as tau goes to 0, f of q goes to e to the 1 over tau. Okay, you can check this for the eta function. You have e to the 1 over 24 tau. If you plug that in here, you have e to the 1 over tau, and here you have e to the n tau. And so when you do the saddle point approximation, you'll get that tau as a saddle near 0 is I over the square root of n. Okay. So when you plug that back, you'll find the exponential growth of d of n. That's how these problems usually work. So the exponential growth of dn maps to the exponential growth of the function itself near what are called the cusps, near when tau goes to 0. But in fact, if you look at this carefully, you only need the imaginary part of tau to go to 0. Okay, so usually, oftentimes it's at tau itself goes to 0, but it could be tau going to some other real number. All right. And now let's study this black hole example that I just showed you. This is the Q plane. So tau goes to 0 means it's here. When you study it, you find that in fact there is no growth. And this was part of the reason for the initial confusion of this problem. But so firstly, the number 3 here appears because in n equal to 4 Yang-Mills theory, the R charges are quantized in units of 3. It turns out that the leading growth is actually at the cube root of unity. That at that point, there's a growth which exactly matches the growth of the black hole. If you study the function here and do the Legendre transform, you get these curves that you see. But in fact, you see that there's also a growth here at the other cube root of unity, other non-trivial cube root of unity, which also has the same kind of real growth, same kind of growth. And the fact is that both of these, there is some real growth and there's a phase, there's an imaginary part, and the real growth is exactly of the same order. You have to add these two. So that there are these two saddle points. One is the black hole, one is some other gravitational configuration, some sister black hole. With, it's related by parity. And you have to add them. And when you add them is precisely how you get these oscillations. Okay? So it's not that you're studying quantum corrections around one. You have to add two things which are contained in the big ensemble. Okay? So that's one comment. But now, if the leading growth is at some root of unity, you might say, why only cube root? Let's test all roots of unity. And in fact, the numbers theorists have been saying this for a long time. So starting from Ramanujan, if you have a Q series of this type, and you want to ask what is the exponential growth, it should look not only as Q goes to 0, but Q goes to all roots of unity. There's a whole field of study in analytic number theory. So you look at that with that kind of guidance. And I can explain why roots of unity and why not an arbitrary number later if you want. And then it turns out that indeed at a generic root of unity, when tau goes to some rational, and there is an exponential growth, but sub-leading compared to this leading. Okay? So now you put it all together. So you want a formula of this type that, you have some gravitational ensemble. This is the index. There was sum over saddles with e to the effective action. And these saddles now are these rational numbers or roots of unity in Q. If tau is rational, then Q is the root of unity. All right. And now you have to calculate it, and there are various methods. And as I said, many people have done it. I've not written all the references. And there are different methods to do it. So you have these functions. You don't have the luxury of modular invariance. You can do, yes.
Why does the localization calculation of supergravity not show such oscillation pattern for the entropy?
Yeah, so here we don't even know how to do the localization calculation. We're far from it.
I see.
I'm only at the n goes to infinity limit. So it's really, so all this that I'm saying is in the microscopic. So this is the sort of semiclassical curves. And I first try to reproduce the semiclassical curves and I see this oscillation. Then
what do you mean real line then? Real line. in the previous page, what
Yeah,
does
that real line is actually the first black hole entropy. So I said that. So the first instinct is to match the black hole entropy. Then you
not the
realize that the
localized-
microscopic is like that. Then you realize that, well, what is happening? So your question is, let's not say localization, but is there a gravitational calculation which matches the oscillations, right? That's a paraphrasing of your question, and you'll see that in a second. I haven't discussed that yet. Okay, so far it's like first one black hole, but then you see that there are two black holes. I'll come to the gravity in a second. This is still microscopics. But already microscopics, there is some amazing thing. So let me just say quickly how to study it. So there are three methods. One is, so as I said, you don't have modular invariance, but you can do asymptotic analysis around every rational point. Or again, you can use some number theoretic method. There's another nice method called the beta ansatz method. And all these, for all these answers, these three methods give the same result. Here's the answer. I don't focus on it too much. Just wanted to show that around each saddle, you get some function of the parameter, the small parameter, the parameter that becomes small as tau reaches a rational number. Okay, so tau tilde is the difference from minus d over c. It's some simple rational function, cubic divided by quadratic times 1 over c. All right, now I put it all together. So imagine you're on some arbitrary point in tau. Okay, so this is the tau plane. Okay, it's the upper half plane. So if you're here somewhere, you ask, take an arbitrary point and you ask, which of all these saddles dominates at that point? You can put this on the computer. Okay, that gives you a phase diagram. Okay, so here what happens is that when you're far, like when you're towards infinity in the imaginary axis, the thing that dominates has zero entropy. This is interpreted as pure radius. Okay, so this is, there's no temperature in this problem, but it's like a temperature. At low temperature is pure radius. Then you start coming downwards in imaginary tau, and you start to see these saddles, and those are the black holes. And these are the two black holes, like sister black holes that I showed you. Okay, they both, so over here, it's the black hole that dominates. Okay, or over here. But here I've cut off imaginary tau at 0.1. You can go further down, and you see this extremely rich structure. When you reach any rational point, is that saddle of the rational point or that root of unity that dominates in a neighborhood. Okay, and it's a very chaotic, I don't want to say chaotic because it's the technical meaning, but it's a very erratic phenomenon. Okay, so as you move along the real axis, these things jump extremely erratically. Okay, and that's your phase diagram, which you can calculate with extremely good control from the Yang-Mills theory. Okay. Now let's come to.
Can you describe some the phases of different colors a bit more explicitly?
Can I describe the phases more explicitly?
Yes.
Yeah.
What kind of the behavior?
Yeah. Okay. So the basic behavior is the if you want, the order parameter can be thought of as the free energy itself. In fact, that's where I was coming to next. Here it is. So if you add all of these together, you get a formula of this type. So each phase is labeled by a rational number. And let's say C is 1, in which case you have the black hole. Then you get precisely the free energy of a black hole. When C is 2, you get the free energy of a black hole divided by 2. That's this one, this and this. Okay, this color coding, Mathematica doesn't give good color coding. It's perfectly symmetric on this axis. Okay, so just like you see it here, there's also a thing here. And just like there's a thing here, there's a thing. Okay, so that's C equal to, sorry, that is C equal to 2. Okay, then that is C equal to 3. Okay, so for each value of C, there is a set of saddles, which gives a free energy, which is 1 over C times the thing. So it's kind of a first order transition. That's the order parameter. Does that answer your question?
No, I was expecting the kind of the how the blue regions are qualitatively different from the
yeah, the blue region
yeah.
has no entropy at all. Here the thing that dominates is just pure radius. There is no horizon, there's no growth of the free energy is 0 here. That's the analog of the deconfined phase. This is like the confined phase with maximum free energy. These
so
are
can
like
you remind me what was tau?
Tau was something that it's not temperature. Remember, it's a supersymmetric black hole, but it's something that couples to the. Sorry, I have to go back. Here it is. is something that, so these black holes are labeled by one charge. This should have been L, okay, one charge L, and tau is the parameter that couples to that charge. That's what I'm tuning.
So
these
is
black
it
holes,
the Lagrangian variable or is introduced by hand?
this variable is the it's not part of the n equal to 4 super-Yang Lagrangian in flat space. Okay? But what we're introducing is a chemical potential. So you put the super-Yang theory on S3 times S1,
Chemical
and then you can
potential.
put a temperature, but you can also twist you can give some chemical potential to angular momentum or to the gauge fields, and that's what tau is.
Okay.
Yeah, and so that's what we're tuning. This is what we can do. We don't have temperature in supersymmetric black holes, but you have other chemical potentials, and you take the simplest situation where there's one chemical potential, and you start tuning it. All right. So this is, if you want, these should be thought of as you know, quantum phase transition. There are zero temperature phase transitions. Okay. So this. Yeah.
Excuse me. So for different C and D, is it different black hole or in the same black hole?
I'll come to that in just a second. So Kisok also asked the same question. I'll come to that in a second. So just to finish the story, so it's here it's like a deconfined phase. Here the free energy grows as n square, and these are partially deconfined phases. The free energy grows as n square divided by c. All right. Now let me make some comments and I'll answer this question. So the first comment is mathematical, that this sum, maybe I'll make this comment second. Let me first answer these questions. Now you ask, what is the gravitational interpretation? And this was answered in this question. That for C equal to 1, we know that there's a black hole solution. There are two types of black hole solutions. For higher C, notice that the free energy goes down by C. So that looks like an orbifold. So it means that there should be a solution with a horizon whose surface area is half the surface area of the black hole, or 1/3 the surface area. And such solutions were constructed by lifting this to string theory. Okay, so these are a whole family of solutions. Okay, so I hope this answers the previous question as well. So there are two black holes which give you the oscillation, plus all of this. And this kind of a formula now we understand both from microscopics and from gravity. So these are not quantum corrections around one black hole. You have to study, you have to fix. So you can ask the same question that was asked, what is tau, in the gravitational theory? And the answer is, you go back here. Sorry about this. You go back to our basic setup. And just like you set up tau here, you also set up tau here. And then study the thermodynamics. Okay, this you do similar to what Gibbons and Hawking did. But there is a subtlety here, which is that at zero temperature, you need a regulator. This question was also asked. You have to regulate the theory and then study what happens as a function of tau. Tau is some boundary condition that you give to this ADS problem. And that's what this gravitational paper did. Okay, that's the, here it is. That's this problem that was studied, and they both give you exactly the same answers. Okay. All still at large n, no like quantum, there's no perturbative quantum correction, but there's non-perturbative quantum, the non-perturbative effects that we're studying. We're asking what are all the saddles. Okay, so that's one important comment. And here I wanted to make a mathematical comment that when I write such a formula, this is similar to this number theoretic formula that I showed you, that there's a sum over of two integers c and d. It's not quite the same because firstly, we don't know if these are all the saddles. We found an infinite number of saddles, or maybe there are more, we think not. But even if there were, this sum doesn't converge. Okay, so it's a mathematical problem. And this problem is very similar to what Hardy and Ramanujan were facing in the 1920s. They also had, when they were looking at partition problems, an infinite set of saddles. And they wrote a sum which was not quite convergent. And what this means is that when tau goes close to an irrational number, this gives you the full perturbation expansion. Okay, that's what this symbol means. So you have complete perturbation expansion. Therefore, when you take n to infinity, you can suppress the non-perturbative effects. So it's really a sharp. So when n goes to infinity, the phase boundaries become sharp. But you could ask, just like Rademacher kind of fixed the Hardy-Ramanujan problem, can we also fix this? Unfortunately, you don't have modular invariance, and this is a problem I've been asking number theorists. And I've been talking to Don Zagier and Stavros Karoufalidis, and there's a mild hope that one can do something like this. There's some notions called quantum modular forms, which might enter the story. All right. So let's get back to physics. So here, so both from the Young-Mills theory and from gravity, you have this set of phases where you can measure the free energy. The last slide. Then it turns out that this kind of a pattern is uniform across all dimensions. I showed you this 5-dimensional example, ADS 5 CFT4, but in fact for ADS 3 CFT2, this was already noticed long ago, and also for ADS 4 CFT3, whoops, sorry, this typo here, ADS 4 CFT3, there is a very similar story that is some upcoming work. Okay, so there seems to be a uniform pattern of the structure of phases. Okay, so I will stop now. I'll just summarize a few points of the discussion. Firstly, that the concrete realization of the Bacon-Stein-Hawking idea is an important goal for any theory of quantum gravity. And supersymmetric systems give controlled setups where you can calculate quantities to high precision, sometimes exactly. Number theory gives an unexpected guide, a non-trivial microscopic guide, which helps us with our gravitational calculations. And then this goes back and forth, as you saw in this N=4 Yang-Mills example. And finally, as I said in the beginning, so somehow the semiclassical gravity arises as the collective behavior of the underlying microscopic system. So in this Yang-Mills example, with all these the fields of Yang-Mills theory, and they all sort of in these saddle points, they come together coherently to make up some large entropy, and they do it in different patterns as you change the chemical potential. That gives you phase transitions. So thank you very much for your attention. Sorry for going a bit over time. Thank you again.
Thank you very much for a very kind and stimulating talk. So yeah, there have been many questions, but yeah, now the session is still open for questions. So please ask a question if you have.
Yeah, I would like to ask one more question. So I appreciate your truly and kind lecture, which is very transparent to outsiders also.
Thank you.
The question is, out of your study of phase transitions, is there any, lesson or possible conjecture which could be implied to finite temperature also?
Yeah, that's a very good question. Well, the most clear answer is I don't know, because clearly all these techniques rely, the details of the techniques rely on supersymmetry. However, what I should say is that this is some ongoing work. It's a long program. You can try to one of you, I think it was Kisok who asked, what's the difference between extremality and supersymmetry? So there is some difference, but they're also very closely related. You can ask, can I do the next best thing, namely to do extremal black holes instead of only supersymmetric black holes? There is some hope. And then you can ask, can I go near extremal? And there's a class of near extremal black holes, which are actually quite realistic. Actually, there's a map of black holes in the sky, the Smithsonian survey, and if you ask, they map roughly the charge, the energy and the angular momentum, the spin. And there are some black holes which, so if you look at the survey, the spin goes from 0 to maximum. There's a maximum allowed spin. And there's some black holes which spin like to 98–99% of the allowed maximum value. Those have very similar behavior near the horizon as these black holes that I'm studying. So there's a hope. It's a sort of long shot, but there's a hope that for that kind of extremal black holes, one might be able to study similar physics.
Yeah, I guess that I got the impression that from your statement that black hole entropy, which is n² behavior, could be obtained from BPS accounting.
Yeah.
means that ground state is as rich as the total spectrum.
That's the point I wanted to make. Wonderful. Thank you for saying this explicitly. Exactly.
Right. So that's how I wanted to now expect that probably maybe within this BPS space, maybe you have some phase transition which is similar to the phase transitions that is occurring in finite temperature.
I see. Sorry, you were asking about the Young's theory. I gave an answer of black holes. Let me discuss that. Absolutely. So that's a wonderful thing. The n square is also present at higher. In fact, the original n square came while studying non-zero temperature. Okay. There, you lose control. You can try to do perturbation theory. People have done that, and of course, you don't have exact results, but you can try to get approximate results. But one thing that I think people haven't studied is to translate these new phases. Ask what happens to the new phases when you turn on a little bit of temperature. That's something which hasn't been studied, and I think that's I've been discussing this with people. That's worth doing. We have a gravitational guide towards the Young's theory, even at non-zero temperature. Okay, so that's an excellent point, and I think that should be done. I'm sure you won't get exact results, but even approximate results along that line would be wonderful. Absolutely. Going by the what we know about the black hole itself, there should be a non-trivial. In the black hole itself, you have an n square. The function, of course, changes when in front changes as you turn on temperature. So I would expect something similar to happen.
All right.
Okay, yeah, time is quite over than usual, but yeah, I'm more happier to listen the detailed one. But yeah, so let me wait. If there is one more question, then please. Or if not, maybe it's good to finish this the good colloquium or lecture.
Thank you very much.
Thank you very
Thank you.
much.
Thank you very much for the invitation.